What is systemd and why it is used by default on most of the Linux distributions? Systemd is an initialization system and systems manager for Linux operating systems. It is responsible for starting and managing user space processes, including system services, programs, and daemons. Systemd provides a standard interface for controlling and interacting with these processes. But how is systemd different from the other initialization systems? Systemd provides a number of features, such as parallel startup of system services at boot time, on-demand activation of daemons, and dependency-based service control logic. Systemd categorizes units according to the type of resource they describe. The easiest way to determine the type of unit is by its suffix, which is appended at the end of the resource name. The most commonly used type of unit is the service unit. It defines how to start, stop, or restart a service, when the service is automatically started, and what are the dependencies to other services. Group of units can be organized into a target unit. The target unit represents the system current or desired run state. The mount unit defines a file system mount that is managed by systemd. The auto mount unit defines mount points that are mounted only when they are accessed. The device unit encodes information about the device in the system. It can be used to start a script on device change, or to define dependencies between devices and other units. The path unit allows you to monitor files and directories for an event. Once the event triggers, systemd can execute a script via service unit. Scope units are not configured via unit configuration files, but are only created programmatically. The primary purpose of systemd scope unit is to group related processes and provide resource control for them. Slice units use Linux C groups to manage and limit the given CPU, memory, disk, and network resources of one or more service units. Socket units allow sending data over a socket to a service unit. For example, a service unit standard input can be set to a corresponding socket unit. Then, the data sent to the socket will be forwarded to standard input of the service unit process. Socket units can also be used for activation of service units. As soon as a connection comes in the socket unit, the corresponding service unit gets started. Swap units encode information about a swap device or file for memory paging that is controlled and supervised by systemd. And lastly, timer units can be used as an alternative to cron. Let's see some details about the service units. The unit section defines unit dependencies. For example, the service unit can be set to start before or after another unit is started during the system initialization, or during startup of the service unit, another unit's startup can be triggered. The service type is defined in the service section. Let's see what are the possible service types. The default service type is simple. A service of this type is considered active as soon as systemd has successfully called the fork function to create a new process. After fork is called, systemd will process other jobs. The simple type is useful when the service starts and keeps running, and the prompt does not return until you press Ctrl+C or stop the service in some other way. If service type is set to forking, it is expected that the process configured with execstart will call fork as part of its startup. This type of service is useful for a process that demonizes itself on its own. Such services return prompt when started, but the service itself keeps running in the background. The one-shot type is used when a service should execute a short-lived command, for example, a one-time setup. With type dbus, systemd will wait until the given bus name appears on the bus. This is useful for services that can utilize dbus as a communication channel. Starting a daemon with forking is the traditional way. Instead of this, systemd offers an alternative with type notify. This alternative is the main process to be the daemon, but in this case, systemd needs to know when the daemon is considered active. For a traditional daemon, this is the time when the init process returns, but this is not possible if we don't fork. Instead, systemd provides a library function called sdnotify, which should be called when the daemon is ready. When this function is called, the service unit is considered ready. A service of type idle is only started when no other dependency units are in state activating. This can be used to try avoiding interleaved command output in the systemd logs. The main purpose of the service section is to define the command that should be started. But actually there are quite a lot of useful options that can also be set here. execstart_pre and execstart_post define commands that should be executed before and after the main process is started. Exec reward defines a specific command which will be executed to restart the service. Restart sec defines a delay before the service is restarted after a failure. Service-specific environment variables can be set with the environment option. There are also quite a lot of settings for monitoring, limiting and prioritizing the CPU, memory, disk and network resources of a service unit using Linux control groups. Some unit names contain the @ sign. This means that they are instances of a template unit whose actual file name does not contain the string part. This string is called the instance identifier and is similar to an argument that is passed to a template unit when called with the systemctl command. In the unit file, it will substitute the %i specifier. There are also more variables that can be used with systemd unit files. Let's see how to control the target units. To list all the loaded target units, whether they are active, running, exited or failed, we can use the list units command. The default target in which the system starts is specified using the default.target symlink. It points to the actual target file that should be reached during system startup. The systemctl getDefault and setDefault subcommands can be used to query and set the default system targets. The systemctl isolate subcommand starts the requested target unit and makes sure that nothing else is running. Linux control groups or C groups are a kernel feature that limits, accounts for and isolates the resource usage for a collection of processes. By default, systemd creates a new C group under system.slice for each service it monitors. This behavior can be overridden by editing the systemd service file and setting a custom slice. But let's see how that works in real life. First, we create a service file. We'll set a simple infinite loop in exec start, which only job will be to hammer the CPU. We'll tail the systemd lock in a new terminal window just to see how it goes. Then we should execute the systemctl daemon reload subcommand to reload the systemd settings and add our new service configuration. After the configuration reload, we can start our service and check if it is working. Let's see what happens if we forcefully try to kill the service process. Remember, we have a restart on failure directive in our service config, and now systemd does the job and starts the process again. We can also check the systemd log for our service using the journalctl command. We can manually restart our service using the systemctl restart command. We can stop our service using the systemctl stop subcommand. Systemctl stop, start and restart commands are useful for starting and stopping services in the current session. In order for the service to run a startup, it should be enabled. Again, we can use systemctl command to enable it. Using the list unit file subcommand, we can get a list of all installed systemd units, together with their current and uninstall state. Let's see how our new application service behaves. It is actually consuming 100% of one CPU on our system. We can limit that using the control group CPU quota option. We should then do a reload and restart in order for the changes to take effect. We can check our unit CPU utilization now. And that's it!